We're gonna start lecturing here on real chemistry. No, I was kidding. I don't have my last time we did obviously some Chem 50 review, and as I mentioned last time, really things if you're looking to sort of review some things, definitely stuff about solutions, stuff about molarity and dilutions is really does come up a lot in this class. We do touch a good little section on some solubility stuff. So, a little bit of a reminder of that. But really, besides sort of the molarity, dilution, that type of stuff, where people really, really do struggle is being able to actually write equations correctly and being able to, like I said the other day, if you're just really given like the two reactants, being able to predict what you get on the other side of the equation is really, really important. In a lot of cases, the reactions and equations will not be given to you. You need to really figure out what is going on based on what is happening in that particular situation. So people really struggle with that. And like I said, they try to kind of make fake it a little bit. You can see on their test, they have no equation written, but they're like, I kind of remember sort of how the math goes. So I'm just going to try to fake the math and stuff like that. So again, just so you know, a part of your grade is obviously writing the equations correctly when we get to those parts. And obviously the math needs to accompany that correctly as well. So we're going to start with kinetics before we, in the next chapter, get really into sort of the big topic of the season. We're going to do a little bit of here on kinetics in this chapter. So kinetics really talks about how fast or how slow a particular reaction takes place. Thermodynamics is another area that we cover in chemistry, and Chem 50 you covered part of that, which is the law of conservation of energy, when you did all that enthalpy stuff, that Hess's law stuff, and again, that stuff should sound familiar to you, I hope. Yes. So when you did all that stuff, that's really about thermodynamics, and we'll have a whole chapter on kind of the rest of the thermodynamics a little bit later on in the semester. But thermodynamics, as we'll talk about when we get there, really deals with the idea of whether or not a reaction takes place. And a lot of times when we think about thermodynamics, we talk about things like, is this reaction spontaneous? And sometimes people, when we talk about a reaction being spontaneous, people have a sort of misunderstanding of sort of what that word means in that context. A lot of times when we think about spontaneous, we think about, oh, that must be like super fast, like boom, snap our fingers and that thing's going to happen. And that's not really, when we talk about a reaction being spontaneous, that's not necessarily really what it means. You can have a spontaneous reaction that does, like you snap your fingers and it happens super fast. Or you could have like a spontaneous reaction that you can sit there all day and the thing is like slowly moving itself along, and it's going to be really, really slow. So it's important as we go through these chapters, when we're talking about things like thermodynamics and we say things like, hey, this reaction is spontaneous, we're not really talking about whether or not the reaction is really occurring fast or slow. What it really does mean is essentially that under these particular conditions, if you leave it alone, it should happen. Basically, it should happen, that reaction. And again, it may happen really fast or it may happen really slow. The area of sort of chemistry that deals with how fast or slow a reaction happens is kinetics. And that's what we're going to talk about in this chapter. And a lot of times we talk about how fast a reaction happens, but I guess in the same sense, you can figure out, how slow maybe a reaction is going as well. So in this chapter is really all about sort of trying to talk about how fast or slow a particular reaction takes place. Now, when we have a particular reaction, a lot of times the way that we express the kinetics of a reaction is through what's sometimes referred to as the reaction rate. And a rate really is, in the basic sense, how fast you do something, right? So there's kind of like you did something and a unit of time sort of association with it. Like when we're driving, right? We were driving at like 55 miles per hour, right? So we're going 55 miles in an hour. That's our rate. We're doing that. We're walking at a rate of 4 feet per minute or something like that. So kind of slow. But when we talk about reaction rates in terms of reactions, very commonly we do reactions where we mix together solutions. So a very common, obviously, unit of solution is molarity, which, as we talked about, is moles per liter. It is moles of solute, right, per liter of solution. As we talked about the other day, it is actually the solute, right, that is reacting when you kind of pour some solutions together to do a reaction. It's that smaller part of the solution that's been dissolved in there that's really what is reacting. Now, when we have a reaction like this, and by the way, S here is seconds. So this is like our reaction rate. That's molarity over seconds. That's basically what we would be looking at, for example, is how the molarity is changing over a period of time. Are we losing it? Are we making it along the way? So if we have a reaction like we see here in the middle, which is A goes to B, A is our reactants, right? That's what they call those things, right? And that's our starting material. B is our products, which is the stuff that is formed. Now, in this particular reaction, it is a one-way arrow, right? And one-way arrow basically means everybody's basically going to be dropping off there on the product side. It's all going in one direction. So as this reaction progresses and starts, the amount of A that I would expect to have, should it be increasing or decreasing with time? It should be decreasing with time, right? Because the only way that you can make products is you have to use the reactants, right? And in a chemical reaction, the only thing that happens is we basically break apart all the bonds, right? So it's all electron based, and we reassemble on the other side. Just by the same token, in terms of B, as time goes on in this type of reaction, we should expect the amount of B to start to increase over time, right? So, we should kind of see A decreasing. At the same time, we should really start to see B start to increase over time as we're making more of it. And we could represent this by what is sometimes referred to as the reaction rate, or reaction expression. I'm going to say that right. Hey, it's been a long layoff, but it's going to be the rate expression. That's what I'm going to say. There you go. So this is what is sometimes referred to as a rate expression. And in this case, we have the rate is equal to minus delta, the change in the concentration of A over the change in the concentration of B. In this case, delta is a change, right, is what it refers to. When we see the brackets, that means concentration. And for the most part, it is molarity is usually the concentration unit that we're talking about when we do that. So in this case, when we look at A, on the top there, that's basically the change in the concentration of A over the change in time. Now, when we do a rate expression there for B, we can do the same thing. The rate is equal to the change in the concentration of B over the change in time. Now, there's a couple of things that are important to keep in mind as we go through this. When we calculate the rate or the average rate of a reaction, it typically should always be like a positive number. So you should always kind of get a positive number when you do that. When we look at A, which is a reactant, we think that it should be decreasing with time, and that is why we actually have the negative sign here for our reactants. So we do put the negative sign in there when we write a rate expression for reactants, because it should be decreasing with time. We do not have that when we look at our product side, because again, it should be increasing with time. So for example, if I were to do a reaction where I have A and B here, and let's just say I'm starting with 4 molar of A and no molar of B there to start with. And I do this reaction at the end, right? We know A should decrease, so maybe I end up with 2 molar at the end. Maybe I end up with 2 molar of B being made on the other side, right? So if I were to just mathematically go to calculate my change in the concentration of A, that is usually your final concentration of A, right, minus your initial concentration of A. Now, in the case of my made-up example here, my initial concentration, my final concentration is 2, minus my initial, which would be 4, gives me a minus 2 molar, yes? The change is negative, it's decreasing with time. That negative there, along with the negative that we should have here, will turn my rate into a positive number, right? So that is why the negative is there. So we'll turn that rate into a positive number when you do that. We could also see why we don't need the negative here, because if we do the change in the concentration of B, It will be our final concentration of B minus our initial concentration of B. And in my made-up example, that's basically 2 minus 0 molar, right? Which is a positive 2 molar. And that means that will give me a positive rate. So we put that negative with any reactant because it is negatively changing with time. Overall, the average rate for a reaction should be a positive number. But individually speaking, if you're talking about the rate of how a reactant is changing with time or how the rate of a product is changing with time, the rate of the reactant will be a negative in terms of change in time because it is decreasing with time, and it will be a positive value there for your products. Any questions on that? And obviously the bottom there where we do the change in time, that's basically how long you ran it for, right? So final time, initial time. So if you started at 0 to wherever you stopped, obviously in that case. So with that being said here, there's a couple ways that we really can sort of follow kinetics in a reaction, but a lot of times we like to see a lot of graphs in this chapter, a lot of diagrams, but here we have A going to B, A represented by the sort of black circles here, and B represented by the red circles. And we can see at really time 0 at the very start of the reaction here. We basically have all reactants, right? They're pretty much all the reactant ones. And as this reaction starts to progress over time, we start to see some red circles or products starting to fill in. We see more products. And at some point, obviously, the reaction will be done. And that's what we graphically see here at the very start of the reaction. It's all products, all reactants, no products. And again, we start to see that increase in products as we see the same sort of decreases happening there. Again, because we need to convert those reactants into products, obviously, to make them. So one way that we can very commonly follow sort of the kinetics of an experiment is to use spectrophotometry. And the basic way that a spectrometer or spectrophotometry basically works is by light and color. So if you have any solution that has a color to it, you can follow the change in color and you can basically figure out sort of what is happening in terms of the kinetics. How it basically works is, right, you set your wavelength to a specific wavelength. It shoots through your sample and it reaches the detector there. We usually measures one of two things, either absorbance, which is how much light gets absorbed by the sample, or percent transmittance, which is basically the ratio of light that went into the right light that reached the detector there. Most of the time we measure absorbance, which again is based on color of the solution. If I have a solution that has a really dark color, would I have low or high absorbance values? You should have high absorbance values, or it's all going to be absorbed by the dark color of the solution, right? And obviously, if I have more of a colorless solution, we're going to have lower to no absorbance values. A light's not going to have a problem. It's going to go all the way through. When we go to select our wavelength to put it to, we always want to select what is sometimes referred to as the wavelength of maximum absorbance. So if you're not sure where your solution would absorb, a lot of times what you would want to do is take whichever solution you're going to measure that is like the darkest, because that guy should have like the highest absorbance values, right? And you would basically measure it at different wavelengths, the absorbance values, and you'll get a chart like this. And usually there'll be like one peak or so, and that is usually your maximum absorbance up here. And that is where you would want to kind of set your wavelength for your spectrophotometer so that when you do your samples, everything should work out good. So let's say we were going to run this thing and I decided I wanted to set my wavelength for all my absorbance values at like 600, which is over here. What's going to happen when I run my samples? You're going to get a lot of errors, right? Because you basically only have about that much of absorbance values that you could take readings before, frankly, you're off to scale. Yeah. Now, if I set it to where it should be, which is over here, I'm pretty much not going to have any issues in terms of when I put it in there, the machine goes error, you can't take that thing out. You'll be able to get all your absorbance value. So it's always important to pick that. And as we use that, maybe on Tuesday and some other experiments, some of the very first sort of procedures that you do when you do that They're a lot more electronical now. They'll make a graph for you that'll look something like this, and they'll tell you, they'll usually will auto select kind of the top of the peak there, or they'll tell you to select the one that's the highest, and you want to do that. By the way, if my solution looks red, am I picking a wavelength in the red spectrum? No is correct. Yes, you would not pick that. So although the solution looks red to us, the color light that's being absorbed is the complementary color to the color that we see. So we would actually pick a wavelength that's not in the red spectrum, but to the complementary color of that when we do it. So sometimes people are surprised, like, hey, my solution looks blue, but I'm not really selecting a wavelength in the blue part of the region. So again, when we see a color on a solution, is the complementary color to what's being absorbed, which means when we use a piece of equipment like this, we will actually be selecting the wavelength to that complementary color of what we see. Now, would this type of process be good for a reaction where everything's colorless? No, because this would be useless, I guess is a better word. It'll be useless because pretty much you'll have no absorbance value on anything, right? So the only reason why we can use this in certain situations is somewhere along the way in this reaction, we have something that has a color, right? So either we're starting with something that's a color and the color is going away, or we're starting with something with no color and then it starts to get a color, right? As you sort of make it. So that is why we could use something like this. So when we look at a reaction like what we see up here, which is the Br2 and a little, I think they call that formic acid, we'll go with that, is Br minus and some CO2 being made. This is pretty much the Br2 color here, and everything on this side is pretty much colorless, which is how we know when we reach here, the reaction is probably over at that point, right? So what happens in this situation is we could take some initial absorbance values. You could take absorbance values every second or have a computer do it for you. Years ago, you used to do those things, but the computer can do it for you, for example, like we'll use in lab, and it could take an absorbance reading, every second. So you mix the two things together, the reaction starts, you should have a beaker that is like that darky red, orangey color there. And as time goes on, as the reaction continues, it will become colorless on the end there. And along the way, you could take all of the absorbance values, right? The reason why absorbance values is important is it relates to our good friend Beer's law. It's equal to BC. We'll go with this one for Beer's law here. There's a few different versions, but this is absorbance. That is concentration. And that is Beer's constant, which is sometimes what is referred to. Sometimes people break that Beer's constant up into the path length and the molar absorptivity, which a lot of times the path length is 1 and stuff like that. So that is Beer's constant. So our concentration in this particular case is proportional to the absorbance value, which is what this shows here. So once again, it is proportional to the change in absorbance value. So the larger the absorbance values that we have, the more concentrated that Br2 solution should have a higher concentration, right? And as it gets converted into products, the concentration of Br2 will start to decrease in that beaker, and we will start to see the absorbance values start to go down as well. All right. So this is a very common way that we do kinetics, and that's how we're going to do some kinetics experiments to start off with when we get there, after we're done with all the common equipments type stuff. But that's a very common procedure that is used. Now, we talk about rates, and if we sort of graph sort of what is happening here in this particular reaction, not that you need to know any of these numbers or anything like that, but what we see here, we have a graph of basically time versus concentration of Br2, which is our reactant. And we do see that over time, the amount of Br2 is decreasing with time, which is what we would expect to happen in this case, since it's a reactant. And there's two types of rate. One is the average rate, which is sort of over a whole period of the reaction is typically your average rate. And that's found by what we were talking about there in terms of Br2 minus the change in the concentration of Br2 over the change in time. And there's also an instantaneous rate, which may be just a pocket of a window into that reaction. So I usually compare it to this when we're driving, say we're driving from here to Arizona or something like that. And, on average, maybe we drive 70 miles an hour or something like that. But maybe there's pockets in that drive, right? If the instantaneous rate should happen for a small specific period of time, maybe we're doing 75, which is legal in Arizona. 80, not so legal. 85, 90, definitely not legal at that point. Or maybe we're in traffic, right? And we're cruising at like 25 miles per hour for a specific period of time to get out of that sort of traffic jam, right? So there could be, as you drive, say, from here to Arizona, pockets of that drive are instantaneous time periods of that time where maybe you're moving faster, right? And maybe you're moving slower, right? But if you average out your entire trip there, maybe you did average out maybe 70 miles an hour for your whole trip. But there could be parts that are moving slower at times and faster. And same thing happens reaction. If you take this like a window into the reaction, maybe it's occurring really fast at some point, but maybe it sort of slows up a little bit as it goes down. If you think like at the beginning of a reaction, you have a lot of concentration of everybody, right? So not going to take a lot of time for them to find each other, right? So at the very beginning, maybe, you have a pretty good rate that's happening that may be a lot faster than maybe what you see towards the end of the reaction when everybody's trying to find each other, right? There's not as much in there. But on average, you might still have a good overall rate as to how that reactant or product is changing over that period of time. So you can, if you have a graph over a specific period of time, take the slope of the tangent of the line, which we won't do in here. It sounds very mathematic, but that's how you can kind of figure out sort of that instantaneous rate for a particular period of time. So if we look at this sort of reaction that we've been sort of taking a peek at, they're sort of instantaneous rates or rates at a specific period of time is not really a constant sort of value, but there is a constant value that you can have. And this is but sometimes referred to as a rate law. And it's a little bit different than a rate expression that we were just talking about. And there is little k here, and little k is the rate constant. And I say little k because the rest of the class is brought to you by the letter big K, yes, which is the equilibrium constant. Yes, those are different things. So make sure you use lowercase k for this one, and everything else when we switch over to the next chapter, use capital K for everybody else. All right, so the rate constant is obviously a constant value, as the name would imply, and it is a constant value that you could get for a particular reaction under particular conditions of temperature. And you could kind of think of it as how fast the reaction is sort of occurring. So if you have a pretty big rate constant, then the reaction is probably proceeding at a pretty good rate. If you have a kind of a lower rate constant value, it may not be moving as fast. So if we rearrange the rate law there and solve for K, you can see here in this very last column, those are all the values of the rate constant for this particular reaction. And it doesn't really matter what time period we sort of take a peek in on at that point. We do get this constant sort of value that is used. The rate constant is an important sort of value in addition to sort of getting an idea about how fast or slow maybe the reaction is occurring. It also later on in the chapter will be a very big indicator of what type of reaction you're dealing with. Based solely on the units that you see for the rate constant, it will tell you if this reaction is like first order reaction, second order, or zero order reaction, which we'll talk about what those are shortly. But it will give you a good indication of what those are based solely on the units. So, and a lot of questions, as we'll talk about, they won't in blinking lights go, hey, this is like a first order reaction, and these are like the equations you should use. But they will give you the value of the rate constant, and based on the units that you see there, you'll know, oh, that's like first order, I should use this type of formulas, or that's zero order, I should use these type of things. Now, what do we do if we have a reaction that maybe doesn't generate any type of color? And how can we follow what is happening? So for example, in this case, although there is color, I think just so you can see it in the picture, but this is all colorless stuff that we got going on here. And in this particular case, it actually generates a gas, right? Which brings up our good old friend there, PV equals nRT. That's the ideal gas law, they call that, I think. And when we use the ideal gas law, right, things need to be in specific units. Pressure needs to be in atmospheres. Volume needs to be in liters, right? N should hopefully be moles, I hope. Or you did something really wrong. Temperature should always be Kelvin, yeah. By the way, to convert to Kelvin, we add. Yeah, you can use 273. We're good. We're friends. We don't have to use the 0.15. We're good. But if you want to use the 0.15, you can. And R is the gas constant, right? Which is our 0.08206 liters atmosphere Kelvin mole. Or maybe you learn 0.0821, which they tend to teach these days. But this one's beat in my head and I can't get it out. So that's the one I use, which is the 0.08206 version. So we do want to make sure, obviously, that we use the correct ones if we happen to need to use a gas law or something like that. But in this particular reaction, because we are actually generating a gas in this case, we can actually follow the pressure here, right? And the only thing in this reaction that would generate pressure is the oxygen, right? And oxygen is a product, which means the only way we can make that product is the reaction had to have taken place, right? Otherwise, we don't have anything. That means in this particular case, at the beginning of the reaction, we probably wouldn't have very much pressure, right? And we would actually start to see an increase in pressure over time as that product is being made. But how can we relate that to sort of changes in concentration and stuff like that? If we take our ideal gas law here and solve for N over V, yeah, that equals P over RT. N once again is moles, right? V is liters. Moles over liters is molarity, yes? So you can solve for the molarity of a gas by simply following, in this case, just the pressure, right? Because R is a constant, and if you did this experiment, you probably would do it at the same temperature, right? Which means it would be constant. So this makes a very convenient way that if you really want to see sort of how the concentration of this gas is changing with time, over a period of time, you could really follow just the change in pressure of that gas, and you can relate it to basically how its molarity is changing per time, which is basically what we see here. And we'd obviously add our time unit to it to give it the more rate aspect of it. So really, by simply doing the change in the pressure over the change in time, that will allow us to figure out how its concentration is changing with time. In this case, we would expect, as I said, it to start to increase over time, right? As it should be being produced in this case. And that's what we see here. This is sort of that reaction, and we got our pressure of really the whole system, but really the oxygen here. And you can see we got pretty much nothing happening at the very beginning, right? And we can see, obviously, as the reaction continues to go on, we see a much big increase there in the pressure. So that brings us to reaction rates and everybody's favorite thing, which is stoichiometry, right? So when we talk about stoichiometry, and we have an equation like this, 2 of A goes to 1 of B there. We basically could say for every 2 moles of A, we will produce 1 mole of B in this particular case. Now, when we're talking about reaction rates, we do have to take into account the stoichiometry of the reaction of what's going on to get the correct rate. So in this case, if we were going to write our rate expressions here, we would take the rate is equal to minus, because A is a reactant, 1 over 2. 1 over the coefficient is where the 2 comes from. So 1 over that coefficient. And if you do the 1 over the 2 in this particular case, when you go to do calculations, that will take into account all of the multiple relationships, the stoichiometry. You don't have to worry about doing it separately or anything like that. So it will sort of incorporate into the sort of the kinetics calculation, the stoichiometry of it, and you don't have to do it separately. You can actually do it separately. You can kind of do some of these problems, as we'll see. You can kind of just do like a mole-to-mole sort of stoichiometry problem and then kind of go into the kinetics part of it. It will all come out the same, but if you kind of want to do it all together, which is sometimes a little bit easier, you want to take 1 over the coefficient. So when we get to the product side here, we're going to take the rate is equal to, once again, because it's a product, there is no negative here. 1 over 1, basically, right? Because that's the coefficient. So that's why we have no sort of 1 over 1. Change the concentration of B over time. So in general, you could write a rate expression by taking 1 over the coefficient, and anything that is negative would be a reactant. Anything that is a product should be positive. You could set all of these things equal to each other using a rate expression like we see down here. And again, we can see for our reactants, we have our negatives. And again, for our products, we do not have our negatives. And we have our 1 over the coefficient in each of these. So what does this allow you to do? Well, it actually allows you to figure out how everybody in a particular reaction is changing with time if you basically just know one thing. So for example, if you know how B is changing over a period of time, you could calculate the average rate. And since B is equal to A there, you can figure out how A is changing with time. You can also figure out how D is changing with time, how C is changing with time. You could write them all connected together like it is there. Or if you're just interested in A and D, for example, you could write them separate to each other. So we were just looking at something where maybe they gave us information about how A is changing with time. We could do minus 1 over A, change the concentration of A over the change of time. And if we're looking at D as well, we want to have 1 over D, the change in concentration of D over the change in time. Now, if I know all this information about A, that will allow me to calculate the average rate for the reaction, which should be, again, a positive number, yes? And this rate here for this reaction and the rate here for the same reaction, is the rate different or the same? They're all part of the same reaction. So the average rate would be the same, yeah? So by knowing about A, that's going to allow me to figure out the average rate for the reaction, which will then allow me to know the average rate for D, right? And now if I want to know how D is changing with time, I just need to multiply the coefficient to the other side, and I'll now know how D is changing with time. So it allows you, if you really just know one piece of information about anybody in the reaction, or if you actually just know the average rate of that reaction, you can figure out how everybody is changing in that reaction. So as I was talking about before, the average rate should be a positive number. But for example, here, if I were to do a calculation and I want to know how just A is changing with time, the number I should get should actually end up being a negative number, again, because it is decreasing with time, and you'll get a negative number. Now, if we calculated for D there over time, that should be a positive number because it's a product. So keep those in mind as we go through it. Any questions about that? All right, so take a moment, write the rate expression for this reaction. Yeah, so that's what the rate expression. So in order for it to be a rate, right, it's got to have some unit of, in this case, concentration over some unit of time. Yeah. Okay, so let's take a look at it and see how we're doing. So here we will do the rate is equal to, we'll start with our first reactant. So again, because it's a reactant, should be decreasing with time. So we're going to start with the negative. The coefficient here is 1, so basically it's 1 over 1, so we don't need to really put it. We will do the change in the concentration of CH4 over time. That will equal our second reactant here. Here we do have a coefficient, and it is a reactant, which means this will be negative 1 over the coefficient there. And that will take into account the stoichiometry that's happening in this reaction. And we'll have our change in concentration of O2 over our change in time. Now moving on to our product side, since it should be increasing with time, it will be a positive number. Once again, here the coefficient is 1, so we don't really need to put it. So this will just be the change in the concentration of CO2 over the change in time. And lastly here, no negative because it's a product. we do need to take 1 over the coefficient, which is 2, to take into account our stoichiometry, change in the concentration of H2O over the change in time. Any questions on that? Here I ran them all together, but you could do them individually. You know, the rate equals all that. The rate would be the same for everybody. All right, so let's take a look at one then where we are going to do a calculation and sort of maybe figure out some things. So why don't you give this a go? For this reaction, the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds and how is. Yeah, so let's take a look and see how you're doing. So in this case, we're given some information about I minus. We have the initial concentration of 1. We have our final concentration here, basically of 0.868. We basically have our initial time of 0 seconds and our final time here of, I guess time, we'll go with lowercase t, is 10 seconds in this case. And we're looking for really the average rate and how the concentration of H plus over time is happening. So there's really 2 things in this reaction that we're dealing with and we should focus on. Obviously, we have some information about our I minus, and we are looking to get over here really to the H plus in this concentration. So a good place to start would be to just write out the 2 rate expressions that go with those guys. So for our I minus, the rate would equal minus 1 over 3 because of the coefficient, also negative because it's a reactant. The change in the concentration of I minus over the change in time. For our H plus, that rate would equal also a negative because it's a reactant, 1 over 2 in this case, the change in the concentration of H plus over the change in time. Any questions on that so far? Now, clearly here we have the I minus information, so that would seem like a good place to start. So we're going to put our information into here because we have all that information. So the rate would equal minus 1 over 3. Change is final minus initial here, which is 0.868 minus 1. That's important because that's going to give me what type of number? Negative, which is going to help me out with that negative that I got going on here, right? So that will again turn my rate into a positive number, which is what we're looking for. You can do 10 minus 0 if you want, or just go 10 seconds on the bottom, whichever way you want to do it. So if we do all that there, 0.868 minus 1 divided by 10 and also divided by 3 in this case, will give us a rate of 0.0044. The units are molarity on top, seconds on the bottom, molarity seconds. This would be the average rate for this particular reaction, right? How everybody's changing over the period of time. Any questions on that so far? That number is good because that is this number right here, right? So which means ultimately here I am looking for how H plus is changing with time. So if I write my rate expression down here for that guy again, minus 1 over 2, change the concentration of H plus over the change in time. I am essentially looking to solve for this part of it, yes? That means I need to multiply the 2 to the other side, but not just the 2, the negative as well, right? So that means that 0.0044 molar seconds will equal my minus 1 over 2 change in the concentration of H plus over the change in time. I'm going to multiply again the 2 and also the negative over there to the other side. That will give me that the concentration of H plus over time is changing at minus 0.0088 molar seconds. Yes, in this particular case. Any questions on that? We see here that when we're talking specifically about our reactant, which is our H plus, and how it's changing with time, I do have a negative number. Yes, so that is negative 0.0088, right? The average rate is 0.0044, which is a positive number. In this reaction, H plus is changing twice as fast as the average rate of what's going on, right? And that is because it has a coefficient of 2, right? So there's twice as much of that kind of floating around. So it will actually affect how fast it's changing because there's twice as much kind of available, right? So it's able to change in that sense. Any questions on that? Yeah. No, not in all cases because well, it is a shortcut if you have the rate. So, but you obviously need to take into account. But yeah, that's essentially how each one would be changing, right? It would be by multiplying them. But obviously, like we had to do to get to the rate, we got to take into account the other coefficients and stuff, right? Other questions? All right. So why don't you try this one? If we have 2.4 times 10 to the 2 grams of NOBR, the molar mass from the periodic table, 109.91 grams per mole, decomposes in a 2 times 10 to the 2 flask in 5 minutes. So again, we might want to start with our rate expressions for each of those. So the rate is equal to -1/2. The change in the concentration of NOBR over time. And the other guy there would be our rate is equal to the change in the concentration of BR2 over change in time. So in this particular case, we have some grams of NOBR that's decomposing. We got some volume. So we need to convert a little bit into some molarity, perhaps would be a good idea. So we're going to look for the molarity here, which are moles per liter. So we got 2.4 times 10 to the 2 grams. We'll use the molar mass that they gave us. Once again, if it was not given to you, you can get it from the periodic table. And that will get us there, 2.4. Looks like we'll call it 2.184 moles of NOBR. We also want to divide it by the volume. So that looks like we have 200 milliliters. We do need to convert it to liters, right? So 0.2 liters there. That's going to give us a concentration of NOBR that is like 10.92, we'll call it here. Yeah. Any questions on that calculation so far? All right. So now that we have the molarity, they do want eventually the time here in seconds, and that's in minutes. So might do a conversion there as well. So 5 minutes, I think still 60 seconds in a minute, give or take 300 seconds. So now I could kind of do my change in time, my change of concentration over my change in time. So if I do this, that's going to give me 300 seconds, and I'm also going to put a negative there, yes. And we'll put that into our rate expression, which is into here. So that would give us that the rate is equal -1/2, negative 10.92 molar over 300 seconds. Why did I put the negative? What was that? Where I got the time? I got it from dividing this, I think. Yeah. Other questions? Why did I put it as a negative? Yeah, it's a reactant, right? So it should be decreasing with time. And if we had the individual numbers, right, to get to those grams, we would take final minus initial, right, which should give us a negative number. And again, that negative is going to turn this negative, right, into a positive so that we end up with that positive rate that's happening there. Other questions? Okay, so I'll put that in there. There we go. Okay, so now we can get the rate here. So we'll do a little 1092 action divided by 300 divided by 2. And that will get us a 0.0182 units molarity per second. Yes, as our rate. Any questions on that there? So now we're really interested again in the BR2 production. So we know that the rate equals the change in the concentration of BR2 over the change in time. And now that we know that that is that answer, that would mean that this should equal 0.0182 molarity per second. Yeah. Any questions on that one? Yeah.
I just took the 10 over that's I would use that on the change in concentration. But in a problem, like what there indicates that that's a change in concentration instead of doing like final minus the mean. I mean, I know they don't give us two values, but is that it?
Yeah. So in this case, what we would be assuming is that's what we started with, and a decomposition reaction, right? It's going to fully kind of break apart, right? And there's no other reactant there, right? So all of it's got to end up on the product side. So that's how you would know that basically the change would be zero at the end, right? So you do zero minus that number, basically. Yeah. Other questions? Yeah. So as I mentioned before, when you do 1 over the coefficient, that does take into account sort of the multiple relationship. You could have done this problem more as like a stoichiometry problem, mole problem, and then kind of incorporated all the kinetics parts. So if you were to sort of take it more like a mole-to-mole relationship, we could actually pick up the problem. We'll pick up the problem somewhere. We'll pick up the problem right here where we just converted our reactant into moles. So we could have at that point done our 2.184 moles of NOBr. And just like a normal mole-to-mole sort of relationship from the equation, we see we have 1 mole of Br2 and 2 moles of NOBr, right? The moles of NOBr would cancel just like you're doing a little stoichiometry sort of problem. And you would end up with here 1.092 moles of Br2. At this point, we can now convert that into molarity by using the total volume and dividing by 0.2 liters. And if we do that, that will give us our concentration of Br2, which would be 5.46 molar. At this point, we can now incorporate our time aspect of it, right, which was 300 seconds to get us 0.0182 molar seconds. So you could take more of a mole-to-mole stoichiometry approach when you do this, or you could just do 1 over the coefficient and kind of does it all together for you, which might save you time. Because really, the reason we do the 1 over the coefficient in this case is essentially, as you can see here, that's the 1 over the coefficient, right? It was the mole-to-mole part of it. So that is sort of why we do that part like that. Any questions on rate expressions? So we use rate expressions to help us understand how everybody in a particular reaction is basically changing with time. It helps us understand how reactants are changing, products are changing. Later on in this chapter, we'll talk about rate laws, which really focus more on just the reactants, not really the products. So this is a nice way that you can sort of see how everybody in a particular reaction is changing. Now, there are several factors that affect the rate of a reaction, how fast or even really how slow a reaction will take place. The nature of the reactants are really important. If you have small molecules, they do tend to react faster than larger molecules. Gases obviously react faster than liquids. And that's because gases are flying around, right? And they also have a lot of energy, which is why they're able to fly around, which means when they hit each other or whatever, they're good to go in terms of all that. Because there is a minimum amount of energy, right, that's required for a reaction to take place, right? So having a lot of energy is very helpful, obviously, for a reaction to sort of take place. And obviously, liquids react faster than solids. Liquids still have enough energy to pass each other, right? The molecules, which is why liquids are fluid. You're able to pour them. When they go into the solid state, they lack a lot of that energy and they lock into sort of solid, which is why solids, right, are hard and stuff like that. But solids can still be reactive, and different types of solids could also be more reactive than others. If you had powdered solids, they're usually more reactive than block solids, and that's because of surface area, right? So if something's spread out, it gives a lot of area where things can start to react, rather than you have a big giant block where a majority of everything's hidden on the inside of the outer sort of atoms and stuff like that. Certain types of chemicals are more reactive than others, like the activity series of metals. So those are like, if you remember, single replacement reactions, right? So when one guy comes in, kicks out another guy, like when you put some zinc and some hydrochloric acid, you get hydrogen gas that gets generated in that case. Remember that for a element to come in a reaction like that and kick out somebody else, it has to actually be more reactive than when it's replacing. If it's less reactive, it will not actually do that reaction. I don't think you guys do the pennies anymore in Chem 50. Do you do the pennies when you like file pennies open, throw it in some acid? No. Used to do that years ago. Old pennies, new pennies. Old pennies, right, were all copper. Yes. New pennies are zinc on the inside and copper on the outside. Yeah. So when you file it and you put it in there, the new penny, the inside is reactive with hydrochloric acid, right?
Paper, right?
Yeah, it will actually, yeah, it will basically, you'll come back and you'll have a hollow penny because you basically ate out the inside of it. The old penny will be great because copper is not going to react with the hydrochloric acid. So they don't do that experiment. They haven't done that, I think, for a long time, but they used to do it all the time. Ions react faster than molecules. We find ions where? Where are ions found? Yeah, they're found in solutions. Yes, they're found in solutions. They're floating around, moving around. Yeah, which means they're good to go, right? So that's basically where ions are, right? It's pretty much the only place you find them is in solutions, right? Now, temperature is a really big factor in terms of the reaction rate. And typically speaking, increasing the temperature will increase the reaction rate. Usually, if you double the temperature, you could double the reaction rate by increasing about 10 degrees Celsius. The opposite is true as well. If you lower the temperature, right, you will typically see the reaction rate start to decrease. And that has to do with that idea of the minimum amount of energy required for the reaction to take place. When you increase the temperature, you're increasing the energy, right? Which means everybody has a lot more energy. You have a greater proportion of molecules that have enough energy for that reaction to actually take place, which means thus it will probably take place a lot faster. When you lower the temperature, you're removing energy, which means there's a less proportion of molecules that have enough energy really for that reaction to go on. And that means you will probably see a much slower reaction rate happening. The Arrhenius equation, which we will see a little bit later on in this chapter, is really sort of the mathematical explanation of that. And we'll see how basically temperature affects rate constants and reaction rates. But that is the general trend that you see. Increase the temperature, you would expect the reaction to occur faster. However, if you decrease it, we'll slow it down. Now, catalysts are things that are also sometimes used to help with reaction rates. A catalyst is not a reactant. It's not a product. It does not get used up in the reaction. It is there really just to facilitate the reaction, in a lot of cases occurring faster. There are some catalysts that will slow down a reaction, but most of the time when people talk about catalysts, they're talking about it in terms of it increasing the rate of a reaction. We oftentimes will find catalysts in reactions on the arrow written. Yeah. Maybe it's like platinum, maybe it's H+, which means it's like an acid catalyst or something like that. We'll oftentimes see those things written up there. There are different types of catalysts, as we will talk a little bit about. There are homogeneous catalysts. Homogeneous, much like homogeneous mixture, means everything is the same throughout. That means the catalyst and whatever is reacting are in the same phase. So they're all maybe aqueous or whatever it may be. Heterogeneous catalyst is one where we have the catalyst and what's reacting in different phases. So Maybe what's reacting are gases and the catalyst is a metal or something like that. That's a solid. So we have those type of things. So how does a catalyst really work? Well, really a catalyst is able to find an alternative pathway for that reaction to occur. So it finds a more efficient pathway, if you want to think about it that way, for it to occur. That's going to allow a lot more reactants to be able to follow that pathway to get to the product. So for example, if you're talking about something, say like a gas, instead of the gas molecules just flying around trying to find each other, maybe you put a catalyst there where everybody's attracted towards the catalyst. Now everybody's in very close proximity to each other, which means it's going to allow those guys to start to react much faster than it would be if they're just like floating around, looking around, trying to find people along the way. So that's very often how catalyst works, is they do find sort of that alternative sort of pathway, more sort of efficient pathway for those reactions to occur. The end result of that is it really does lower the overall energy demand on the reactants to get to the other side of the products, and that allows a lot more people or reactants to get really to the other side to make those products. Any questions on that? Now, concentration is a really big factor in terms of how a reaction takes place, or maybe if it does take place. Usually the larger the concentration of reactant molecules, the much faster the reaction will take place. Just by simply the larger the concentration, that means you would have a lot more of those guys available to react, right? So again, they're not going to have to go hunt around to find people. And when we talk about concentration, obviously in the sense of a solution, molarity is really, again, the moles of the solute over liters of solution. So if you have a large molarity, you have a lot of solute, which is the stuff that's dissolved in it, and really the things that are reacting. So you have a very big concentration of those. So again, they're going to come in contact with each other a lot quicker than if you had the opposite. If you had a really low concentration, it's going to be very sparse out there for trying to find somebody to react with, right? There's not a lot in there floating around. Concentration of gases depend on the partial pressures of the gas. Higher pressures usually result in a higher concentration of the gases. And when you have a high pressure, what does that mean in terms of volume? Do you have a high or a low volume, a high or small volume, large volume? Yeah, you do have a small volume, right? When you have a high pressure. So if you just think about gas molecules, if you have a high pressure, that just shoved everybody right next to each other, right? So that's going to allow things to react a lot faster, rather than if you have a lower pressure, right? You'll have a little larger volume maybe, and it'll take a little longer for everybody to find each other in that space. So pressure, volume are all related to each other in terms of how fast a reaction takes place or not. All right, so let's talk a little bit about the rate law, which, as I mentioned before, is a little different than the rate expression. The rate law will really express the relationship of the reactants to some type of power. So here is what a generic sort of rate law would look like for this reaction, our equation that's up there. The rate is equal to K. So as we talked about earlier, that is our rate constant. A is our concentration. X and Y, these are what are referred to as orders. And orders are sort of like the proportion of those guys that is needed for this reaction to maintain a specific rate that you got to throw in there. You can actually calculate the overall order of a reaction by adding those together. Orders are found experimentally. They are not the coefficients in the balanced equation. So you have to take experimental information to be able to actually calculate a rate law. So rate laws are really calculated by experimental information. They're not really calculated just based on the balanced equation or anything like that. So what is a rate law on orders? You know, how maybe is it applicable in like real life-ish type of deal? So let's say we did have this reaction, like the rate is equal to K, A to the X and B to the Y. And by the way, as we can see here, the only things included in the rate law are reactants, no products. So no products in the rate law, just reactants. So let's say we have this reaction, and let's just say, for example, that the orders of A is 1 and the order of B is 1 in this particular case. That would mean that the overall order of this reaction is 1 plus 1, which is a second order reaction, is how you would determine that. Now, there is usually only, as we'll talk about, certain types of orders of reactions that we come across commonly. 0 order, first order, second order is very common. And a lot of it is based on, if you just think about most chemical reactions that you maybe have come across, there's maybe 1 reactant, 2 reactants, maybe 3, right? So we don't get a lot of the reactions that there's like, 6 reactants happening all at once or anything like that. So because of that, the way that they will come together is in these kind of general types of overall orders of 0, first and second type order reactions are very, very common. Occasionally, maybe a third order type reaction or something like that. So if we have something like this, and since this guy right here, which is our rate constant, is a constant value, when I do my calculations here, I'm not going to really even worry about putting that number in because it'll be the same for all of them, right? It's the exact same number. So if I multiplied something by 2 in 9 different places, they all got multiplied by the same number, so we can eliminate them. So let's say we did one experiment here, and we had for the concentration of A 2 molar, and for the concentration of B, we had 2 molar, right? And we throw that into our rate law with our orders, which are 1 for each of those. We would have a rate in this case, basically 2 to the 1, right? And 2 to the 1, which would give us a rate of something like 4 molar, and we'll just call it seconds. We'll put the time part back in. So we'll call it something like 4 molar seconds is this, right? So let's just say this reaction happens and you go, well, kind of taken a really long time for this reaction to happen. I threw these things together and I'm growing older by the second waiting for this thing to occur. Maybe I want to like speed this reaction up a little bit, right? So let's say I want to do this experiment again. And I go, all right, what I'm going to do in this case is, in this experiment, I'll keep A at 2 molar, but I'm going to toss in there twice the amount, right, of the second reagent, which is B. So now when I put it into my rate law, this will now give me 2 to the 1 and now 4 to the 1, which gives me an overall rate of like 8 molar seconds. Yes. Did I speed up the reaction? I did, right? My original reaction with my concentrations happened at 4, right? I doubled one of the reactants. What happened to the rate? It doubled as well, right? So now this reaction is going to happen twice as fast, which is, yeah. What decides it is experimentally determined based on the reaction. So we're gonna do some problems on how to calculate it, but it's based on experiments, and it's only really discovered or calculated through experiments. So it has to be experimentally determined. Yeah. All right, so that's good. But let's just say, for example, all right, maybe I mix these things together and, well, it was like way too fast for me to actually take some readings, which, by the way, will happen to some of you in the kinetics experiments because you'll be mixing things together and taking too long to put it into the spectrophotometer. And by the time you get it in there, the reaction's over and you have a dead patient. It's like no absorbance value. It's just a dead line going across it. So sometimes when we do experiments, just the process of mixing everything together and trying to get it into the spectrophotometer to take some absorbance values, you want a little bit of time to be able to do that the reaction is not done, so you could actually take some proper measurement. So let's say we were doing this and we want to slow it down. We could very simply, right, just change our concentration of A or leave it at 2, but we'll drop our concentration of B down to, say, 1 molar in this case, right? Now, in this case, the rate would equal 2 to the 1 and 1 to the 1, which is now 2 molar seconds. So by taking my concentration of B and cutting it in half, what happened to the rate from my original experiment? It's now half as fast, right? So it's slowed down by a factor of 2. So by knowing the orders of a particular reaction, you can really sort of dial in that reaction to how you need it to use it by using the kinetics of it. If you see like you're trying to do some measurements and it's like, way too fast, you could change the concentration to try to slow it down, that you could actually take some readings. Or if it's taking way too long and you need it to occur a lot faster, you could play with the concentrations to speed it up. And the orders play a really big role in that. Let's just say we took our same reaction here, and let's just say instead of the order for A will still be 1, but let's just say that the order for B happened to be 2 in this case rather than 1. So let's go to our same reaction here that we originally started with, which was we're going to use 2 molar of each of those. So when I put it in now, the rate is equal to 2 times to the first power. And now this is going to be 2 to the second power, right? Because the second order for B. That's going to give me 4 times 2, which is 8 molar seconds, right? This reaction, because in this case that B's order is actually second order, happens twice as fast as our guy that B is first order, right? So this is really important. Now, when I have a reaction like this, right, where one is, say, second order, one's first order, the one that's going to make the bigger effect on the rate is second order, right? So if I really want to slow it down or I really want to speed it up, I would probably play with B's concentration here, right? But maybe I just moderately wanted to kind of increase it or decrease it, I could play with A's, right? It would still maybe increase it, but it wouldn't have as big an effect if I kind of played with sort of B's concentration. Make sense? Questions on? Now, what happens if I had an order, for example, where A was 1 and B was 0 order, right? So let's do our same first experiment here. The rate would equal 2 to the 1 and 2 to the 0. When you take something to the 0 order, what does it equal? It does equal 1 in this case, right? So in this case, because the order of B was 0 order, my rate is 2 molar seconds in my made up example, which out of the gate is half as fast as the place where they were both 1, right? So the different orders for these different reactants, and obviously I just focused in on one, right? Can have an effect on how fast or slow reaction takes place. You could use it if you know the orders to sort of manipulate your reaction to have it sort of work to your benefit in a lot of cases. By the way, in this particular case, if it was A is first order and B was 0 order, and I decided to do an experiment where I really wanted to increase it. So A would be at 2 molar and I did B at 18 molar because I really wanted to increase it. Would I increase the reaction rate? I would not, because B is 0 order, which means you could do whatever you want to be. It's not going to have any effect on the reaction rate, right? So it's not going to change anything. So in this case, I would foolishly put 18 molar there and go, wow, it kind of did the same thing as it did before. In this case, the only thing that will affect the rate is A in my example, right? You would have to do something to A to affect the rate of it. Any questions on that? Yeah. What's it? Technically speaking, in real life situations, common orders are 0, 1, 2 that you find. In textbook problems and problems that are made up, you technically have an order of anything, to be honest with you. But very unlikely to have orders that would be in real life really high. Because if you just think about it, for example, overall orders of reaction, right? In order to get, say, a first order overall reaction, if I had one reactant, all right, it could be first order, right? If I had 2 reactants reacting, one would have to be first order, one would have to be 0 order if you add them together to get the first order, right? So, if I had second order, You could have one reactant where it's second order. You could have two reactants. That's maybe first order in each, right? Would give you second order. So if you're trying to talk about maybe like an overall order of a reaction of like 8, right? You would need a lot of guys reacting to get yourself to 8. And in most cases, as I mentioned earlier, most reactions, if you think about it, okay, I got like one reactant, maybe 2, maybe 3 on the outside, but you don't typically find lots of reactions where there's lots of individual reactants happening. And you would need that many reactants to really get a super overall order. That's a really large number. So in theory, yes. In practicality, probably in most cases, that's why we usually focus in on overall orders of 0, 1, and 2 for the overall reaction. And individually, for individual reactants, usually that kind of 0, 1, 2, 3 maybe.